Welcome to a lesson on multiplying negative numbers. When I was in the 6th grade, my teacher showed me the proof for why the product of negative numbers was a positive number. She just showed me the proof once, but I spent days doing that proof over and over again because I was so excited about the discovery of something strange. Mathematics, where things were obvious, was being used to discover things that were not the obvious. Decades later, I realized there was a lot missing in my education. There were things that I didn't understand. And over the time, I saw some proofs that were given with manipulatives. One of the proofs was assuming that you had a rectangle with negative sides. Somewhat absurd, to me at least, but some people were using that as a proof, and then showing that with this impossible manipulative, that negative number times a negative number is a positive number. But I do accept in that. It's nice to see different ways of trying to prove the same thing. It helps build up better confidence. So what I'd like to do is to show you what it takes to really understand the type of negative numbers and what you and I were missing all these years of our lives. So let us begin. So, mathematics is a process in which we use the obvious to understand the not so obvious. The rules of mathematics have to be used judiciously if we want to get the right answer. So let's start off with the 3 things that we need to understand to prove that the product of negative numbers is a positive number. First, a negative number is the added inverse of a positive number, something that you may not have heard in your lessons in school. Only real numbers can be negative. We'll understand that shortly in this lesson. Multiplication is a count of the number of times we add a number to 0. Extended multiplication is not a count or an error. 0 is the number before 1. 0 has the identity property in addition and a null property in multiplication. You'll notice that we had to qualify each one of these statements that are going to be important to us. For the general rules, we have subtraction is inverse addition. So we can check subtraction by reversing the process. Division is inverse multiplication, except for the number 0. Aha, the quicksand of mathematics. Why does 0 misbehave such? And this is what begins to scare us in mathematics, when these surprises come up that we don't quite understand, but we make an effort to try to understand. There are 5 properties in mathematics, 4 of which are conventionally taught. The other one is somewhat assumed. The first is the associative property, which says no matter how we group our numbers, we get the same answer. The commutative property says we can change the order and still get the same answer. 0 is the identity property for addition, and 1 is the identity element for multiplication. We had to state those as basic postulates because we can show that they work for integers, but we just have to assume they work for other numbers. And the distributive property is when we multiply a sum by a number, and then the answer is the same as multiplying that number times each number in the sum and summing up those sums. And the transitive property is says a quantity can be substituted for its equal in many cases. Sometimes I'm a little bit uncertain about the transitive properties. So, to begin, we have to understand the basic elements. We have to understand what 1 is, 0, and negative numbers. Well, that may be silly to you, but I had trouble understanding those until I started playing with them. 1 is used to make the integers. So 2 plus 1 is 3, 3 plus 1 is 4. You notice we add a number to the number before the number of integers, and we get that number. So, what's the number before 1? Well, I'm going to assume it's something called z. So 1 plus z is equal to 1. Now, I take 2, which is equal to 1 plus 1. I substitute for one of those 1's, z plus 1, use my associate property, and I get that 2 is equal to z plus 2. No change, just as it was for 1. And so we have by induction that z added to any integers will give us the integer as a result. Aha, z is equal to 0. We are going to assume that when 0 is added to a decimal, irrational number, and a complex number, that it remains the identity element for addition. That's why we had the properties. As I've shown it here, but I don't know how, or have not tried to do it for numbers other than integers. And let us now define multiplication. 3 times 5 is equal to 0 plus 5 plus 5 plus 5. 3 is the count of the number of 5s that we're adding there. Later we're going to have to assume that multiplication is going to be redefined to handle decimals, irrational numbers, and complex numbers. So this original definition gets us started, but it's not complete. And you'll notice I've also changed it by throwing that 0 in there. Okay, so 2 is equal to 1 plus 1. Substituting 1 plus z for each of those 1's, regrouping them, I get 2 plus 2 times z is equal to 2, which is also equal to z plus 2. This is where I get a little bit flaky with the transitive property. So z must be equal to 2 times z. So we now have that 2 times 0 is equal to 0. What about 0 times 2? Well, if we have 3 times 2, that's equal to 0 plus 2 plus 2 plus 2. Dropping 2 of those 2's, we're left with 0 plus 2. And dropping 3 of those 2's, we're left with 0. So 0 times 2 equals 0. We also can arrive at this by using the commutative process, giving us confidence that 0 times any number is 0. Well, that takes care of 1 and 0. What about negative numbers? Well, let a be the number before 0. We know what to do there. A plus 1 equals 0. We subtract 1, we get a is equal to 0 minus 1. And now we define a shorthand notation. 0 minus 1 we'll call minus 1. We did that with multiplication. 0 plus 5 plus 5 plus 5 was written as 3 times 5. And now if we substitute minus 1 back for a, we get minus 1 plus 1 equals 0. Well, let's look at the number before a. Well, add 1 to that number, that'll give us a. Now add 1 to both sides of the equation, we get b plus 2 is equal to a plus 1. But a plus 1 is equal to 0. So now we find that b is equal to minus 2. And we get minus 2 plus 2 equals 0 through substitution. We're now ready to find a negative number. When a negative number is added to its positive inverse, we get the additive identity. We assume that decimal and irrational numbers can be negative, but not complex numbers. So, before we do our proof, since negative numbers is something new for us, we want to see what the rules are. Read not so obvious from the obvious. So, we notice by our definition that negative 1 plus 2 is equal to 0. So oops, I made a mistake in that slide there. So this minus sign should have been a plus. Nice that the instructor to make mistakes makes us feel a little bit better. Negative 2 is equal to 0 minus 2. Well, that's how we define negative numbers. But suppose we subtracted the negative number. We get 2 is equal to 0 minus minus 2. Aha, a discovery. When a negative number is subtracted from a number, we get a positive number. Rule number 1. Let's try something else. The identity element, 2 plus 0 is equal to 2. Subtract 3 from both sides. Now group the 0 minus 3, and we can replace that by minus 3. So when we add a negative number, it's the same as subtracting a positive number. Rule number 2. And now what happens if we add negative numbers? Well, we take the definition for negative 3 and negative 5. We know that added to its inverse, this is 0. We now commute them to get the negative numbers and the positive numbers together. We group them, and then we take one of those groups, the 3 plus 5, which is 8, subtract it, and that gives us minus 3 plus minus 5 equals 0 minus 3 plus 5. But 0, when we subtract a negative number from it, gives us a negative number. That's our transit property. So we now show that when we add two negative numbers, we add them as positive numbers and put a minus sign in front of them. Well, we did this last part so that we can show what happens when we multiply negative numbers. 5 times minus 3, using our rule, we repeat minus 3 times. Well, we know when we add 3 to itself, negative 3 to itself, we get negative 15, which is the same as 3 times 5. So multiplying in the positive number times a negative number, we get the result as if we're multiplying positive numbers with a minus sign in front. And by the commutative property, minus 3 times minus 5 should also be equal to a negative number. Now, there's another way we could do that using the distributive property. 0 is equal to 0 times 5. 0 can be replaced by minus 3 plus 3. Use the commutative property, and we get minus 3 times 5 plus 3 times 5. Well, if we take and subtract the minus 3 times 5 from 0, or subtract the 3 times 5 from 0, that gives us 0 minus 3 times 5, leaving us with minus 3 times minus times 5, which we know is minus 3 times 5. And minus 3 times 5, we know can be written as minus 3 times 5. So we've now shown that it doesn't make any difference whether we're multiplying by a negative number or multiplying the negative number, it still works. And now for the proof. We start off with 0. Minus 3 times 0. It's the identity. 0 is the identity property for all numbers. Now, we didn't quite prove that a negative number times 0 is still 0, so that's where our identity thing comes in. And minus 3 times replacing the 0 with 5 plus 5, that's the transit property. Now we multiply by 3 using the distributive property, so we get minus 3 times 5 plus minus 3 times minus 5. And now we group those two, and noticing that minus 3 times 5 can be written as minus 3 times 5. And now we subtract that minus 3 times 5 from the equation, and we get minus 3 times minus 5 is equal to 0 minus minus 3 times 5. Subtraction. And we now know that multiplying negative numbers gives us a positive number because 0 minus minus 3 times 5 can be replaced by 3 times 5. We will assume that this is true for decimal and irrational numbers. However, it's not true for complex numbers. Minus I times minus I is equal to I squared, which is minus 1. Here, a negative number times a negative number gave a positive number. This is somewhat circular reasoning because we defined I to break the rule. We can also take comfort in the negative complex number is not defined. Remember, when we defined a negative number, we use a real one to create them. What about the manipulative approach? In our conventional world, we do not really have negative lengths. Thus, using the rectangle with negative lengths is somewhat artificial. Thus, we learned that our fear for mathematics is justified. However, if we remember, mathematics is a process in which we use the obvious to understand the not so obvious, then we develop approaches through practice and focusing on the rules that allow us to overcome those fears. Thank you for spending these few moments with me, and hopefully I've helped make you feel more comfortable with math or want to become more comfortable with math.